This question is from GATE Mechanical Engineering of 2014. This is question number 48 of set 3. The question is, a double pipe counterflow heat exchanger transfer heat between two water streams. Tube side water at 19 liter per second is heated from 10 degrees Celsius to 38 degrees Celsius. Shell side water at 25 liter per second entering at 46 degrees Celsius. Assume constant properties of water, that is, density is 1000 kg per meter cube and specific heat is 4186 joule per kilogram Kelvin. That is, the logarithmic mean temperature difference in degrees Celsius is. So let's first understand the working of counterflow heat exchanger using a suitable diagram. Now suppose these are the two tubes, the below one and the upper one, and the cold fluid is entering from here. Let's say this be point B and this be point A. The cold fluid enters here. So the temperature of cold fluid is Tc in. So let's write Tc in, and exits from here. So let's write Tc out. Okay. So the temperature of cold fluid at the exit. Now this is the middle one is the shell in which the hot fluid enters. So let's write here Th in, and at this point at B it is Th out. Okay, so in the middle we have hot fluid and here we have cold fluid. Now let's represent the variation of temperature from point A to point B of the hot and cold fluid. Now in this diagram, the yellow line represents the hot fluid and the blue line represents the temperature variation of cold fluid. Okay. Now since this is a counterflow heat exchanger, as the name suggests, the flow is in counter direction, opposite direction. The cold fluid enters at Tc in and exit at Tc out. Hot fluid enters at Th in and exits at Th out. Now from the conservation of energy, we can say that the heat lost by the hot fluid will be equal to heat gained by the cold fluid. Therefore, we can write mH, the mass flow rate of hot fluid, into C, the heat capacity, multiplied by Th in minus Th out should be equal to mass flow rate of cold fluid into C, the heat capacity, to Tc out minus Tc in. Okay. So for hot fluid, we know the mass flow rate, since the density is same, so we can write the volume flow rate. So this will be equal to 25 for hot fluid, 25 liter per second, multiplied by 4186 multiplied by temperature of hot fluid at the inlet. So that is 46 minus Th out. That will be equal to 19, the volume flow rate of cold fluid, into C, that is 4186, because we need to assume that these two are equal. The properties of fluid are equal, multiplied by 38 minus 10. So from here we'll get Th out, the temperature of hot fluid at the exit will be equal to 24.72 degrees Celsius. Now actually we need to calculate the LMTD in this question, that is the logarithmic mean temperature difference, LMTD, which is given by temperature difference at the inlet minus temperature difference at the exit out in divided by ln theta in by theta out. Now let's calculate theta in and theta out. So theta in will be equal to temperature of hot fluid at A minus temperature of cold fluid at A. That means Tha is nothing but temperature of hot fluid at the inlet, okay, which is 46, minus the temperature of cold fluid at the exit, which is given 38. So this value will be 8 degrees Celsius. and theta out will be equal to temperature of hot fluid at B minus temperature of cold fluid at B. So temperature of hot fluid at B means temperature of hot fluid at the exit, which we have found out to be 24.72 degrees Celsius, minus temperature of cold fluid at B, which is temperature of inlet of cold fluid, that is 10 degrees Celsius. So theta out will be equal to 14.72 degrees Celsius. Now we can calculate LMTD. See, even if we change the order of theta in and theta out, we'll get the same result. Okay, so theta in is 8 minus 14.72 whole divided by ln 8 by 14.72, and this value of LMTD, the logarithmic mean temperature difference, will be 11.02 degrees Celsius. Okay, so let's fill in the blank. So the LMTD will be 11.02. For more information on LMTD, you can refer to the NPTEL course lecture number 6, double pipe exchanger 1 on process equipment design by Professor Shabina Khanam of the Department of Chemical Engineering at IIT Roorkee.